Hi everyone, welcome back again to Fiddy Technologies. So yeah, in I actually very sleepy. I'm very sleepy right now. It's 12:45 a.m. in the morning. But I'm curious about something. So this video is not gonna be about like a normal tutorial that we have in this channel. I just want to try something, and while I'm trying it, I record it so you can learn what I learned today. In fact, I don't know if it's gonna work or not. So let's see. So what I'm gonna do, I mean, the most important things that I want to see is if cohesive element works with extended finite element or not in Abaqus. So I did many simulation with extended finite element in the past, and I know how to do it. Maybe I need to see some YouTube videos right now because I forgot. But the idea is that I did it before and it was very easy. And I also did a lot of cohesive element simulations. The only things that I never combined both of them at the same time. I knew that it it should be working because I saw several papers simulating, for example, micromechanics simulation where the interface between fibers and the matrix were modeled using cohesive elements, and the crack in the matrix uh, is modeled using extended finite elements. So yeah, I know exactly that it should be working fine, but let's see. So the things that I want to simulate right now is this. I mean, I checked this. So it's called core shear crossing. Is basically you have a sandwich where the core is much softer than the skin, and the skin is usually made of something stiffer like aluminum or composite. So basically, you make sandwich. If you don't know, if you're not from mechanical engineering, you make these sandwich structures because you want to make sure that you have a large moment of inertia. So when you are doing banding, it's really good because then your how you call it your cross section is big, right? So if you calculate the inertia, I equals 1/12 bh to the cube. Yeah, your h is way big because yeah, you have this large cross section, and it's light because the how you call it the core is made from foam because they because they're not supposed to sustain any load. Yeah, because when you're doing banding, the maximum stress is on the skin, not in the natural axis. Natural axis has zero stresses. So why put materials there, right? That's why we put core, a foam core, or a very soft core. So okay, anyway, I talk too much. I said I don't want to talk too much. Here there's a crack here. We call it delamination, the core and the skin, and then the core itself has a crack, and this crack is inside the core. So we want to model it using not cohesive, sorry, because we don't know the exact location. So we don't want to use cohesive elements because cohesive element abacus here is basically the the predefined cohesive elements, right? I forgot what is the name of the predefined one. Is it intrinsic cohesive element or extrinsic cohesive element? I think it's extrinsic, intrinsic. I don't know. Anyway, you need to define the cohesive element location first, and then the cohesive element will grow its crack when needed, right? But here we don't know the exact location. It can slightly change. So we want to put something that can be adjustable, like a extended finite elements, right? But I just checked the extended finite element in Abacus, in YouTube. I mean, and most of the tutorial in YouTube, they have this what you call the crack location, so the initiation side. So you need to tell them this is the crack, the initial crack, and then the XFEM will take care of it when then will extend. But that's not something that we want, because if you need to have initial crack and then you have the same limitation as cohesive elements, you need to put them there from the beginning, right? We don't want to do that because this crack here in the core should appear naturally, all right? So let's try. Don't talk too much because this is not a tutorial. So I explain what I remember because I did it a lot of, I mean, back in the past, long, long time ago. We're going to model it using 2D, right? 2D planner. Okay, I think it's good. I think the size will be 300 by, I don't know, maybe like 300 is like, okay, yeah. And 100 maybe, okay. Oh, okay, yeah. No, no. Yeah, okay. Maybe we need to edit. Let's make confix here. Sorry. Fix. So this not gonna move. And then we edit the dimension because I made a mistake. Let's make dimension here. Maybe 50 is good, right? Yeah, 50 is good. Okay. And click done. And then what you need to do is to split it, right? Because we want to input cohesive elements between the face, between the skin and the core. Maybe here, partition face by sketch, yeah. And then I want to put 4 lines, 1, 2 here. Okay. There's another one here. Okay. There's another one here. Okay. There's another one here. You might wondering why there are 4 lines. Yeah, because cohesive elements. The core, the skin will be 2 millimeters. Yeah, 2 millimeters is enough, right? So let's do it from distance from here. Oh no, I yeah I want you click here, you click here, and then the vertical distance is 2.0, while this guy to this guy the vertical distance should be 0.001. Yeah, because they are like, I mean, they are cohesive elements, right? And then where's the other one? There should be 4, right? Why I only, I think I created, hmm? Really? I think okay. And then okay, I just press Control Z to undo, Control Y to redo. Okay, so don't get confused. Okay, and then let's make another one here from here to here. Okay, and then no, here from here to here again 2.0, and then let's make from here to here. It's 0.001. Okay, so it's very, very, very thin. And then you click X and done. See? Done. Now what's next? Let's make another part. It should be you know, a shell, a wire. Maybe no, less shell is good. This one up, up, yeah. Okay, and then we make dimension. Radius, I'm not sure. Radius is 5 is enough maybe. And then we will cut it half from here to here. Okay, click escape. All right, and then you click here. Where is it? Trim, auto trim. Yeah, you remove this guy, you remove this guy, you remove this guy, you remove this guy, and then you get, you call it semicircular. Yeah, this is will be the hinge. Okay, because we want to do this kind of simulation, 3-point bending, right? And then let's go to the properties. This is the most important part for the pinned, okay. we're going to give a steel, I'm not sure, 200. Let's make the dimension is MPa, millimeters, right? So it's 200,000 MPa. All right, it's for steel 0.3. That's for steel pin. All right, and then you make another one. You call it a composite skin. Okay, they're still elastic, right? And now we use, I'm not sure which one. Oh yeah, this one. No, not lamina. Orthotropic. Which one is the engineering constant? Yeah, so you use, let's say, for example, you're using glass fiber polypropylene 34 600 or 600 or 600 for 600. So they are transversely isotropic because two direction and three direction are the same. And this one is 0.34, 0.34, 0.4. This is 1700, 1700, and then 1450, because one is a fiber direction. So shearing in 1 2 and 1 3 should be more difficult comparing shearing 2 3, because 2 3 you don't have fiber, it's only matrix dominated. And that's it. I don't need any damage. Do you think I need damage? No, right? Yeah, no. And you need to put another one, core. The core is a little bit difficult, I think. You need elastic. I'm not sure what kind of values I need to pay. Let's say 3 GPa, 3000, and Poisson ratio is maybe 0.4. You should use something related to foam, but it's just a trial. I mean, I'm not really sure what should I use. Oh yeah, you should model it using this guy, because we want to use the how you call it? Why I forgot the extended finite element. So this is maximum principal stress. So we want to make sure at 20 MPa this guy will crack. 20 MPa, 20 MPa, okay. And then you have damage evolution. It will fail at 1 millimeter. Yeah, maybe 1 millimeter. Yeah, okay. And then put some stabilization a little bit, 0.001. Okay, I think should work, right? I'm not sure. Let's try. That's the point, to try. And create section. This is easy. It's just a normal step. Yeah, first section is the steel pin. Second section is a composite skin. Third section is just a core. Then you sign to this guy. This is the pin. Where was it? Yeah, steel pin, the material steel pin. Okay, that's how you check it. And part number one, you signed to this guy. It's a no steel pin. Yeah, composite skin. And to this guy, also not sure, composite skin. To this guy, you said core. Yeah, that's nice. But then now we forgot to do something. The cohesive element here. Okay, we create another material called cohesive. Mechanical elasticity. Young modulus should be 200,000. They're very stiff. The Poisson, maybe 34 600 is enough. Was you don't use isotropic. You use fraction. So this is first 600, 34 600. This is not material property when you're doing delaminations using cohesive element. This value, this stiffness value, is not material properties. Okay, it should be an artificial value that is so large so to ensure continuity displacement between the core and the skin before damage. Okay, so we want to, how to say, we want to erase the effect of cohesive elements before the lamination happens. So when the lamination hasn't started yet, the cohesive element should not give additional compliance or additional stiffness to the problem. So yeah, if you read papers, they will call it spurious compliance problem. Spurious, spurious, yeah, SPURIOUS, spurious compliance problem. Yeah, so to remove that problem, we need to put something that is so stiff to ensure the discontinuity between the skin and the core. Yeah, I don't know what I'm talking about. I know. Uh, Mechanical and traction separation law and quadratic stress is 20, 20 MPa, okay? And then damage evolution 0.1, and then put the same stabilization here 0.001, no, 0.1. Okay, so now it's set, damage set, quad set. Okay, it's nice. Okay, this is the cohesive, and you create here, but you use other cohesive than material cohesive, response traction separation, and okay, and then you assign to this guy. Okay, section 4, I think, right? And then where is it, the one below here? So if you want to scroll, you use this scrolling guy, I don't know, the wheel of your mouse. Okay, section 4 too. So now we're good, right? We are very good. So now assembly, that's it. You assemble. There are two parts. Okay, and then there's another part. I want to offset them, and then I want to offset another one. Okay, so I'm not sure. Okay, I'm so lazy, orienting this is like, something that I don't really like. Instance, this guy from 0,0 to 10,0, so they move. Oh, that's too small. Maybe 100. Oh, 100 is too big. Maybe 50. Okay, 50 is good. I think it's good. And then click OK. And then after you shift 50, you, okay, no need. Just this guy now. You from 0,0. Now you want to go to the left, minus 50. All right. But this is from 0. This is not from 0. It's okay. I don't care. The point is that I want to do 3-point bending. It does not necessarily to be like perfectly 3-point bending. I want to introduce non-symmetry here so that my crack will not exactly in the middle, because that's the point, right? I want the crack appears somewhere that I cannot predict using the classical method like cohesive elements. That's why I'm using XFEM. So it's okay. And then I want to remove this guy a little bit from 0,0 to 5.001. Hey, no. Back. It's 0,5,001. Okay. So they are only slightly. And then you set this guy. I want to rotate first. Oh, no. Okay. Yeah. This guy. moves here. Okay, okay, and then I want to, where is it? I want to rotate. I want to rotate this guy. This is the axis of rotation, 90 degree, 180, I think, right? Yeah, good. And then I want to translate this guy. So this guy meet this guy. Okay, nice. So now it's good. Everything. Save it first. Abaqus, CZM, XFEM. Okay, just in case. So I can also record the Python script to be used later. What's next? That's it, right? Yeah. And then step, create, static general. It's okay. Non-linear geometry, no need. Automatic stabilization, yes, just in case. Make it 100,000. Make it -10. Initial 0,01, because I have, here I have like a gap, so I just want to make sure that the gap will close first. So I want to make sure the initial increment size is small enough. And here, because I want to see the crack evenly spaced, and I want 200, very fine. And I think I need to do something here. I think here, where is it? Volume, not volume. Volume also good, just in case I need to do something later on. Cork will make your ODB file big. Hey, where is it? I forgot. Sorry, guys. There is like level set. Yeah, pi. Level set value for pi and psi. If you're interested, we'll make another video later. Comment below if you're interested to know what is this guy. This is related to the extended finite element. Okay. Let's SDG. I'm not sure I need it. Yeah, you need it because you have cohesive elements, right? Damage initiation criteria. Okay. Anyway. Okay. And then I need to do it for the energy too, just in case I need the energy later on. Okay, just save it so I can get the journal file later. So if you want to know what journal file means, check my other video about Abaqus Python scripting. So basically, once you make it manually like this, in the future, you can just simply like automate the process. You can just simply change it to the size of the pin, the size of everything else, the material properties, how many pins you want, and modify it using Python. So check the series on Abaqus Python scripting. And now here, this is important when you when you're simulating damage, always set this guy because, usually the default simulation is not enough. You will always end up in errors in like too many attempts. We did, but actually they don't attempt too much. They attempt 5 times here. They cut this time step 5 times. Still didn't work. They said, okay, I'm give up. But when you do damage simulation, you need very small time steps. So I easily increase it to 20. If you need, you can improve using line search control. 10 is, I'm not sure it's hell, but just click it. Okay, interaction. I did it. Interaction, not yet. So I don't like it. Yeah, first make the contact. Create interaction. Surface to surface. Okay. The master here and here. Okay. Finite sliding and contact interaction. We make contact interaction film. So mechanical tangent penalty with 0.2 and normal. Yeah, and contact. Okay. Okay. And then you can also make here service to service contact, the master here, the surface here, Same thing, same properties as before. 0.2 column friction here. Oh, I'm so sleepy, guys. You might wondering why my voice keeps slowing down, keep lowering out, lowering down. Sometimes I don't even realize what I say. It's okay. Let's do it before sleeping. That's it. That's it. Yeah, there's one thing that I want to do here in interaction. I think you need to create special. Yeah, a crack, not a sim crack. Create XFEM. Yeah, this is continue. Select the crack domain, single instance, geometric face. Okay, I want this part only. Yeah, yeah. Okay, done. Nice. Allow crack to growth. Specify contact properties. Yeah, and the crack location none. Yeah, I don't wanna. Yeah, let them decide. Because this is what I said in most, when you search YouTube video, they always give you the contact location here, the crack location here. I don't want to give crack location because I don't know where the crack will start. All right, let's see if it works. The load. Okay, so here it's easy. Displacement. We fix this guy. Pump, pump, pump. So they will not move. Same thing here. Pump, pump, pump. They cannot move. All right. And then this guy. Let's see the picture. You see that it moves around the thickness. I mean, this indenter moves from here to here. So it's basically it moves like travel through the thickness of the how you call it, this guy. We make it 50 before, right? So thumb make it 50, guys. I think minus 50 is because it's going should be down. Okay, nice. And then mesh. There's we'll make mesh on part. Let's make it a little bit finer. I don't know, I don't like this kind of mesh. Make it smaller because I like my work to be smooth and nice. Yeah, good, right? And then part one. Here we need to make a control. Sign mesh control overall because I want to make sure that the stacking direction of the cohesive element is correct. So I want to use sweep and quad. Redefine sweep path. This one, accept highlighted. Yeah, accept highlighted. Okay, accept highlighted. They're correct. Okay, accept highlighted. Make sure there's nothing pointed towards the horizontal side, right? Because our cohesive element is facing above and down. Accept highlighted. Okay, nice. Okay, and then make it maybe 0.5. Not sure how long it's gonna take, but yeah, it's okay. And then we give element type for this guy and this guy and this guy. We give it not cohesive, it's a plain strain. Secondary accuracy, use enhance to avoid hourglass and click OK and done. Okay, and then we did it again, but this time only for this highlight first. Okay, for these two. Continue. We're going to give them cohesive. Viscosity, I'm not sure you need to put it there. Lemon dilation, yes. Maximum degradation. How much maximum degradation? 0.999. Just to avoid the one, because when you choose one, usually you will have problems. Diffusion by 0. You divide the stiffness by 0 because you remove the total stiffness. I think I need to choose one thing again. Where was it? in step here to make sure that the coins development will be deleted. I think you need to, I'm not sure which one. Oh yeah, the status, yes. Status, and what's there's again the cards, yes, the max. Okay. Oh, that's it. I think it's good. Status, yeah, I mean status. And job. And save first. Make sure it's correct. Create job. Then prioritization use two and submit. I'm not really sure it's gonna work. Let's see if it's working or not. Bum, bum, bum. Should be straightforward, but it is not. It is not straightforward. See, it errors. An answer material with without. Oh, okay. I need to give a. See, that's how you read error. That's what we learn in this channel. And isotropic material properties with a local oriented system have been defined. So you need to something wrong with the orientation system. We don't even assign an orientation system. Or for the skin, we need to go here, assign material orientation. So which one is that? This one and yeah, both of them. Let's do it one by one. Set one. Use uh, we use coordinate angle 0. Okay, continue current system. You can leave it like this, but I don't like. I mean, because I want to get the Python script. So if I just use like this, my Python template will not give me the ability to change the angle. But if I use this guy and then I put 0, and then later on, if I want to make it 90, I can just simply change this one because then Abaqus will give me output template for Abaqus Python scripting for these kind of things. But if I just use this one, that's it. They will give me global and with this default value, no way I can change it. But here, it's a good thing. Okay, and done. Let's try again. The hope is still there. I think it should work. And I'm already very sleepy. 1:17 a.m. We have spent, I don't know how much, 33 minutes. Okay, I'm not sure how long it's gonna take, even if it's working, right? Just, oh, see, not yet error. Hopefully it will not error. No, no, no. I think you also need to do something in the interaction. You after you do, you have a crack, right? Crack one. You also need to do something like interaction manager. No, no, create initial. Yeah, XFEM crack growth. See, we didn't do it. The crack one. Okay. Then we need to change it again. Okay. Yes. But it's nice. It's running, right? So submit again. Okay. All right, guys. So let's see if it's working. And while I pause this video, so it's gonna be shorter. Okay. Yeah. In the beginning, it says that there are 4 unconnected regions. Yes, because there's 1, 2, 3, 4, and on the plate itself, the sandwich itself. So there are 4. It's correct. Just a warning, right? And there's displacement increment is too big for contact is too big. Yes, because we give them like a very big maybe like gaps, so they feel like there's a 0 because it's like pushing flying object, right? But you see here in the beginning is 0.001. They cut the time step 4 times. and then they increase again. They start to stabilize, increase 0.005, 0.08, 0.01, 0.1, 0.0. Yeah, now it's increasing again. So now we have our first plot, I think, right? Our first frame. You can already check the result. Oh my god, what the hell? Why the hell is it like? Oh, I don't like it. I don't like it. Is it because of this? Sometimes this guy, oh, auto compute, it's one. You sure it's one? Oh, it's 60, right? So make sure you put uniform because Abacus exaggerate everything if you don't set it right. It looks good. Looks good. Yeah. So here we have four frame right now, but this is not the point, right? I mean, the context simulation is not the point of this simulation. We want to make sure that the crack appears using the extended finite element and then propagates toward the skin, and then the cohesive element will start to, yeah, to active SDG still zero. So that area is still 0.3. So it's like 30% of the starting point. I'm not sure where they will start. Let's see. Uh, I hope the simulation will work. Okay, I will pause again the video because it's going to take a long time. Okay. Yeah, guys. So if you see here, it's still progressing. It's normal that when you have a damage simulations, the time step goes to 10 to the minus 4, minus 5. That's really, really, really normal. Uh, do you see here that, yeah, we have some damage here. It's in fact cohesive elements, not cohesive elements. Why? It's XFEM, XFEM. Yeah, so nothing, 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 and then they start to appear here. So in fact, appear so many cracks, right? They divide one elements into two parts. So multiple crack occurred at the same time, and they grow, and I think they will tend to make a like this, like a triangle. Yeah, yeah. So I'm gonna stop the simulation because this is not what I expect, right? I mean, if you see here, we might need to change like the shape of our. I'm not sure. This doesn't seems like a pin. It's like a rectangle. That's why they can have this kind of crack, or maybe it's because that our pin is way too small that we need to make it bigger. But I'm already very sleepy tonight, so yeah, we'll see tomorrow. We're going to modify this tomorrow, hopefully, because I mean, it's one good thing is that the simulation works now. There's no convergence problem. The settings works fine. The damage can occur. One of my concern before that, you always need to put your initial crack when you simulate the XFEM. It turns out that without putting any initial crack, the cohesive, no, not cohesive, why I call it cohesive again, the XFEM can grow by themselves, so they can appear in the area where the stress reaches the threshold, right? The maximum stress that you define in the material properties, and that's good. That's one thing, but the problem is that this is not the kind of the setup is wrong, right? I'm pretty sure it's because the pin size is way too small, so you know you don't have this kind of things, right? Because I want to have like this delamination here, and then yeah, they go here, they make this, this, how you call it, the transverse crack, and then they will create another delamination here, because here, if you see here, it doesn't seems like that, right? Yeah, so tomorrow we are going to re not redo, like modify the setting, like for example making the pin larger or making the specimen thinner. Let's see tomorrow, and hopefully today's video is helpful for you and you enjoyed. Don't forget to click like, subscribe, and share. And see you tomorrow, guys.